All right, I'm starting this lecture a little bit early, namely several hours early. We'll try to do the mic check first. Hang on. Okay, I'm trying to do a test here. I'm not sure what's going on here. Hang on. There is audio there, but it does not seem very loud. Give me a second and I may plug in a microphone. And I will switch mics. All right. Okay, now I'm doing another mic check with a different microphone. Okay, now there we go. All right, we've got it. Okay, so in class the other day, I made a mistake and I was solving this problem. Basically, I had a 15 millimeter diameter copper coil with a solar hot water heater. The average temperature was this, which that did not actually matter. It went through that speed, which that did matter. It had a density and a kinematic viscosity right here. It said take E over the epsilon to be that. My biggest problem came when I divided these two numbers. If you take this and divide that, that's not what you get. This is what you get. So instead of E over D of 0.06, it should have been 0.002. The rest of the problem, you can watch the video. There were 11 tubes and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elbows. He did not consider elbows in the losses, but if you go down here, instead of putting this as E over D, you put that, you solve this out, you get still the 12,000 for the Reynolds number, which came from right up here, which to me seemed fairly small, but that's okay. You get a friction factor of 0.03 here, and then you put in the friction factor and you get the correct head loss. So that was my mistake, simple mistake. This can happen to anybody, but for some reason I probably typed this in the calculator, just probably why it ended up being wrong. And so there's that one. Let's go and span through taking a look at the next one, which actually the picture, let's see if I can get the picture here. And I'm going to go ahead and keep working on the same page here. Here's what I got. Take that. Let me go over and get the picture and drop. Okay, hang on. Okay. Okay, and what I'm going to do is come over here and drop it, say, right there. It's very tiny, but there's not much I can do about that. But I can zoom into it, and that's what I'll do. Okay, this one might be the second problem. And the second problem, it says water is pumped from a river from a river through a corridor. Okay. Here, let me get the echo off behind me. Okay. It pumps through a 45 millimeter diameter hose having a length of that. It tells you what the friction factor is. So you don't have to use Moody diagram here. And it says the gauge pressure, vapor pressure for the water is that. Okay. Now, in this one, there has to be an assumption that has to be made. Here's the scenario. Hang on, let me get give me a second. Okay. And this is kind of a weird, oh, there it is. So in other words, as you draw this water here up this pump, eventually when you get right here to about B, this will be the lowest pressure in the line being sucked into the pump and then dumped out here on the ground. That being the lowest pressure, there is a possibility that the water can boil. As you well know, when you were in thermo, if you drew an 80-degree Fahrenheit water down to around, I think it was 0.2 psi absolute, it will start vaporizing. That can happen in a fluid. Now, what he has told us, now this is something that's very interesting here, since he has told us a pressure which is negative, this means that this pressure, vapor pressure, has to be gauge, because there is no such thing as an absolute negative pressure. It has to be gauge pressure, meaning if it was 14.7 psi, for example, and that's atmospheric, and it just so happens you're at 4.7 psi, and this is absolute for both, and say it boiled or it vaporized here. The water vaporized here, so it's going to have to be a higher temperature than 80 degrees, and he doesn't tell you the temperature here. Then this is actually 10 psi gauge, which usually a G is not written there, but it's a minus 10 psi gauge. So this is a vapor pressure that is a gauge pressure. So how do you do this problem? He tells you, okay, so he tells water is pumping from a river, okay? That's the hose, that's the length, friction factors, and the gauge vapor pressure is this. Suppose that H is equal to 2. What is he asking you? Determine the maximum volumetric flow rate. Okay, so what you do is, again, you write between A and say maybe B. Okay, well, there's already a B there. PA over gamma plus ZA plus VA squared over 2G minus FL over D, V squared over 2G. This is your energy at that point. This is the loss going through that pipe, and this is the energy. It's actually the energy per unit volume at point B. Now, a couple things you can do. You can make these simple assumptions. One, at A is the top of the water, pressure would be 0. You could set it as your datum. You could say the river is fairly large compared to this small pipe. And so what you'll get is minus F L over D V squared over 2G equals to, what's the pressure at B? Minus 98.7 kilopascals. And you'll want to, pull those units out. Gamma. He has told us H is 2 here. 2 plus velocity at B squared over 2G. Turns out the velocity in the pipe and the velocity of B are the same thing. So what you end up with, this 2 meters, is the fact that he told us that B was 2 meters above A. And so what you end up with is putting this term and this term together, maybe putting them this way, 98.7 times 10 to the third newtons per meter to the cube. Let's just make sure this is supposed to be a minus, because what I'm doing is I'm taking this, moving it to this side. I'm going to take this term, I'm going to move it to that side, and gamma, 9810. Unless he told us a density, I'm going to assume rho is equal to 1,000 kilograms per meter to the cube, which gives me that G is equal to gamma is equal to rho G, or 9.81 times 1,000, which will be 9810. And that's what I'm putting right here, minus 2. Equals to, And I'll just take the V squared. That's going to be your V squared here. I'm going to put, well, I can put V2 over 2G because there's a 2G here and there's a 2G there. And then what I'll do is I could put a 1 here. And then I'll say plus F L over D over here. But what I want to do before I leave you here with the rest of the problems, I want to make sure that this number 98700 over 9810 minus 2, I just want to figure out right offhand what that value is. Shouldn't take me but a second. It's about 8.06116, and that's going to be equal to the V squared over 2 times 9.81 because it's in SI units. Diameter 45 millimeters. Okay, hang on. 1 plus, he said 0.028, 0.028, length 2.5 meters over diameter, I believe, of 45 millimeters. Let's see, e to the minus 3. And so all you have left there is to solve for V. So you solve for V, you go through the process. You're going to have to take, once you get your V, to actually find the answer you put in, you will have to go in here and multiply it times your area to get your Q, because this is what he's asking you for. Oh, he doesn't. This is just a statement. The question is over on the thing. And he says, determine the maximum volumetric discharge from the hose so that cavitation will not occur within the hose. Okay, so that should get you going there. Let's look at the next one, which is hang on, just let me kind of get the picture in the statement. So what I'm going to do, go down under here and get myself a picture and a statement. You'll have to bear with me while I get the picture and I get the statement. Okay, so first I'll get the statement, and I'll come to about right here, about right there, and I'll do a paste. I'll come back and get the picture, and put the picture right there, say. And what does he want? He wants to know the power output of the pump. Okay, so before I do that, let's go and look at the information. First thing, he made it easy. Oops, sorry. He made it easy for us. He gave us that. He gave us this. He gave us the water delivered. Okay, and then the length of the hose. So let's look at the picture. And he wants to know, what was it? Oh, the power. Okay. So, hang on. He's going to ask us for the power. More than likely, the best thing to do is, since you're in the SI, you're probably going to want to determine your power in watts. So here's what you're going to do. Okay, your pump is obviously pulling the water out of there and up the hill. So he has a couple of labels here, C and A. So let's start with C, which is right here. PC over gamma plus ZC plus VC squared over 2G. He is going to add or put, okay, so how does he phrase this? I'll call it head by the pump minus the loss in the pipe, F L over D V squared over 2G, V being the V in the pipes. And you're going to end up at PA gamma plus ZA plus VA squared over 2. Because the length of pumps is a friction factor is that. Okay. So a couple things. And here I'll go ahead and do these. You know, I could look at B. That's not really going to be that much information, but I can look at A and C. I'm going to make a couple of assumptions about A and about C. Okay, so A and C. And what I'll do is the pressure, the elevation, and the velocity. Okay. So at C, this is a big long reservoir. I'm going to assume that this is a very large bunch of water compared to the diameter of that pipe. So you're not going to be drawing that surface down that much. It will be shrinking, but it won't be shrinking that much. Elevation there, I'm going to assume my datum starts there, which immediately puts that at 5. I'm going to also assume that the water squirts out into the air. Okay, hang on. This is as far as I can zoom in. Okay, so I'm going to assume the water squirts out into atmosphere. This is atmosphere here, which basically tells me, hang on, that the pressure at both C and A are nothing. And so now the question is, I got V. Do I know V? Well, he tells me V, okay? He tells me the velocity coming out up there at A. Whoops. So if I want to know the velocity, okay, so let's go ahead and strike these out. C, zing, zing, zing. All of C gets knocked out. I still have the head of the pump. And I'm going to have F, so I'm going to go ahead and fill in. F being that 0.018, length 10 meters, diameter 45 meters, 45 e to the minus 3, velocity, whoops, don't know, 2 times 9.81 equal to, okay, so let's look at A, for example. Nothing, 0 plus 5, because it's up here at 5, plus, here's the deal, V squared over 2 times 9.81. However, he told us the water being delivered is 0.0. Okay, so maybe I should do this to the side. 0.004 cubic meters per second, which is the same thing as the velocity over pi, diameter of 45 e to the minus 3 squared over 4. So this will give you your velocity. You can take this and divide by this. I could try it. I'm not going to be interested in multiplying it myself, but if, okay, the phone thing will do that. Let's see if, because I'm not interested in typing all this in the computer, but let's see if the phone can figure this out. Okay. 0.113177. Not sure if this is correct. You better check. But I'm going to go with it. The key is you have that, and you have that, and you put those in. You move it to the side, and you'll get the head of the pump. It'll just be a number. But as it turns out, if you go in and you want to know the power, power of the pump is going to be equal to gamma times the flow rate times the head, which usually is written, sometimes it's written as H, but it's the head of the pump, H pump. And so this is going to be the power that you're going to be extracting back out of here. You're going to want to make sure it's in watts. Now, in SI, in regular English is foot-pounds per second. Over here, it's going to be Newton meters per second. You better check, but I think that's a watt. So that's the layout there. Let's see if I can hit the layout on the next one. You'll have to give me a second. I have to look and see what it looks like. Okay, now I will need to get a picture here. It's a very weird, okay, here we go. Okay, again, I'll put down the picture first, and I'll just put it right there. And then I'm going to grab this, put it right there. Okay. So it says 2 water tanks are connected together. Here. 2 water tanks are connected together. They're connected together. 2 water tanks are connected together using 100 millimeter diameter galvanized pipes. Take epsilon to be that, and the viscosity to be that. Now, that doesn't tell me what he's asking. Let me go back. Oh no, I don't want to do that. Sorry. Hang on. Okay. He says, what is he asking? Okay, let me go back one more step here. I think I jumped the wrong way. Maybe I better just take what he's asking and copy it, because it's too much to say here. Okay. Okay, this is what he's asking. He says, determine the flow out of tank C when both valves A and B are open. Neglect any minor losses. Using an iterative solution, trial and error. For the first iteration, assume the friction factor of each pipe to be equal to about that. Oops, sorry. To be about that. Then he says use this. This is going to be your replacement for the Moody diagram for a particular value there. Okay, so since, okay, did I actually use the iterative term? First iteration for each pipe to be equal to that. Okay. Now, we get rid of this on the other screen. Have to give me a second here. All right. So here's your deal. I'm just gonna let's see. Okay, yeah, he tells me here and he tells me here. So I'm gonna go between here and here. PC over gamma plus ZC plus VC squared over 2G equal to minus FL over D V squared over 2G equals to pressure at D gamma plus Z at D plus V at D squared over 2G. I can make a couple. I have enough space here. Pressure, elevation, and velocity at locations C and D. I'm going to assume these are fairly large. I'm going to assume he has a port right here, so it's atmospheric. And my question now becomes, who and where do we want the datum to be? And I've picked this one because it's the lower. And then I come down 3, go all the way across, and up 7. That tells me that's 4. Okay, so ZC is 4. Everything else is 0. So here's what we're going to do. I'm going to rewrite this down. I'm going to move this over. Minus plus, silly, V squared over 2G. Now here's your problem here. Okay, so now let me do everything I can first, but let me kind of make a statement here. I'm going through 2 water tanks. And I'm going through using this. Both valves are open. Here's what's funny. It's hard to see, but here's a valve and here's a valve. Both of them are open. Hang on. What is interesting is if we look at this here, I'll make a diagram down here. You have a pipe, comes across, it goes like that. It looks like it's 10 and then 8. He doesn't say anything up here. So it's 10 meters, and then 8 meters. let's assume that through this pipe we had, let's just say, 1 cubic meters per second. Now, he says this is 9. So what you have here is essentially 9 in length and 8 in length. Now, what is legitimate is that you can go through either one of these pipes to get to D in the Bernoulli's equation sense. But the key is you're going to lose energy in going through either one of these pipes. There might be a different flow rate through one through the other. And so how do we address that? Interestingly enough, what you have to do is you have to come back, and this problem may be too much for us for right now, but this is the same pressure on each pipe. Did he label that point? He did not. So technically he's supposed to, or we're supposed to, recognize the pressure here is the same. So, but I can go straight through that point to end up at the other end, D. So it's kind of like a circuit. But if I had 1 cubic meter per second here, then these two come together. So let's do it this way. I'll say this is pipe, how should I say it? Pipe 1, this is pipe 2, and this is pipe 3. So the volumetric flow through pipe 1 is equal to the volumetric flow through pipe 2 plus the volumetric flow pipe 3. So the water gets split into 2 parts, 1, 2, and 3. The question is, if I can go down either one of these, which one do I go down to get there? In other words, Bernoulli's equation says I go down here and I write the equation to here. Well, I only have to consider the pressure drop in this one. But Bernoulli's equation also says you can go down through here, like here, and I get the same thing. So what we really need is we need to put 2 of them in which, these 2 are together. So in other words, here's what I've got. 4, that's the difference between this, is equal to F. Now, he says, okay, so we're going to set the friction factor equal to that 0.025 for both to begin with. So I'm going to say this. I'm going to identify this as pipe 1, length of pipe 1, the diameter of pipe 1, V through pipe 1 squared over 2G plus the friction factor through pipe 2, the length of pipe 2, the diameter of pipe 2, the velocity through pipe 2 squared over 2G. That is if I went through this pipe and up through here. Well, I can do this. Here, I'll do it this way. Since I have the magic here, I can do this. I'll do a copy, and I'll do a paste. And I can also go exactly through this. And what is going on here? Okay, that is not That's not the escape button. Okay. Okay, hang on. Oh, shoot. Okay. Okay, now, give me a second. Okay. What I have done here is I have decided to go from here and go through pipe 3. So I have two equations here. Both of them are legitimate, both of them are correct, and both of them are okay. It's just I need now to convert. I don't need to, but it might make it easier if I could convert the velocities to the q's. In other words, velocity is equal q divided by area. So this is what I'm going to do. I'm going to go in, and I'm going to do this. Put area squared. Now, all the pipes are the same. Let's see if I can touch that. All the pipes are the same diameter. So I can just put area here, and that'll classify for all of them. Let's see. Q over area squared. See if we can barely touch that. Q over area squared. And Q over area squared. Now, here's what's so interesting. This one, okay, let's think about this. Now, there's a different F for each one of these. So I've got two of these that I can work on. And basically go in, and I can go through this the first time. The first time, he says, take it as 0.025. Okay, so if the friction factor everywhere is equal to 0.025, what do I get? Okay, so he really wants you to know, he wants to know Q. Okay, but how do you do this? You're going to have to break the part and recognize, actually, as I'm looking at what he has done, I think he may not have done this one correctly, because he made an assumption that was incorrect. I think I'm going to have to give everyone credit here. But the way you would do this is you would go insert it here first, and your first equation, let's see if I can go ahead and just write this for the first equation. 0.025. The length of the first one is 10 from this 10 meter here. The diameter is the same for everybody, 100 millimeters. So I'll just do 0.1. And then you get Q1 squared over 9.81. And then now I've got to come up with the area squared. The area is going to be pi 0.1 squared over 4. Let's see if I can put that in. See if I can figure it out. That's really weird. Okay, 0.00785, or I can just leave that in there as a pi 0.1 squared over 4. Then what you can do is you can turn around, copy that same thing, copy, and we will paste it. And when we paste it, we're going to recognize that it is now length 2, which is 9. It is going to be Q2. Diameter is the same. Everything is the same. Okay. Next thing we do, we take this. Now, it turns out that just like here and here, they are exactly the same. This one, however, is not, because it is 8 meters and it is 3. So now Q1 back to the original is equal to Q2 plus Q3, which means I can do one of two things here. And I don't know which of the two we want to do, but I can do this. Q2 is equal to Q1 minus Q3. And I can take that and put it in right here. If I did that, here's what I would see, okay? Let me do this. I would see, here, let's get rid of this, and I'm going to copy this entire equation, and I'm going to move it down here, and then what I'm going to do, I'm going to zoom in here, I don't know what's going on there. Okay, I'm going to erase that. I do not know what that is, but this would be, here, let's do this. Oh, shoot. We'll move it to the side out here. And I'll say Q1 minus Q3 squared. If you look at this wonderful equation, in this one, you have two equations and two unknowns. I do not think he solved this correctly. So I will go ahead and hit the give full credit on this one. As a matter of fact, I'm pretty sure this was not. Let me see, how do I do that? Hang on. Let's see. Hang on. Bear with me. Oh, here we go. No? Okay, there we go. Here we go. Oh, wait. Let me give full credit on this one somehow. See if I can figure out how to do that. Okay, so I push this button. Bear with me as I try Well, huh? 6 people completed that. I don't buy into that. Okay, well, we'll skip over that. I'm going to let that one span its way out. I can't do anything to the end. Hmm. It's not even listing the numbers correctly. Well, I'll look at this and we'll deal with it later, but something's up over here. Oh, there's the button. Okay. Okay, well, I'll come back and address this later. But we're good for now. I'm just going to draw it to a close.